Hello, my name is Pan from Zhejiang University. Today I'm going to present our work, Differentiable Design Galleries, a differentiable approach to explore the design space of transfer functions. Direct volume rendering, or DVR, is a powerful and effective visualization technique for exploring and studying volumetric data. The expressiveness and flexibility of DVR stem from the large design space of the transfer functions, which map points sampled from raw volumetric data to visual properties, such as color and opacity. However, finding an appropriate transfer function is difficult for inexperienced users. In the past 3 decades, a lot of work are proposed to help transfer function design. Some of these works propose and exploit the idea of design galleries to ease the design process of transfer functions. The core idea of design galleries is to generate a sufficient number of exemplars to span a transfer function design space, and arrange them in a certain way, allowing users to explore and choose among the presented possibilities. However, several problems limit the usability of design galleries. First, when users already have a specific design style in mind, there is no effective method to query the target design within the design space. Second, it is unclear how to efficiently navigate the high-dimensional transfer function design space. Merely using dimensionality reduction is not enough since a lot of information is lost during the projection process. Third, it is infeasible for users to modify the rendered image they are interested in, unless they revert back to using the traditional transfer function widgets. To address the aforementioned problems, we propose differentiable design galleries, a transfer function design approach based on deep learning and differentiable rendering to assist users in exploring the design space of transfer functions. By leveraging a latent design space, users can engage in various types of transfer function exploration, including querying, navigation, and modification, without resorting to explicit transfer functions. Our approach consists of 3 main stages. First, given specific volumetric data and a predefined transfer function design space, we generate design exemplars using a traditional DVR render with randomly sampled transfer functions. Then we train an encoder and a generator to generate a latent design space based on those design exemplars. Every latent code in this space represents an implicit transfer function design. Second, we propose a set of tools to help users explore this latent design space and integrate them into an interactive interface. Third, when users are satisfied with a certain design, we leverage a differentiable DVR render to reconstruct the design explicit transfer function. To ensure that the latent design space is well organized for subsequent explorations, we tailor an imitation task to train our networks. Given a DVR image of volumetric data as a design exemplar, an experienced DVR expert can analyze the features shown in the design exemplar and guess the underlying transfer function. If the guess is good enough, the image rendered by a DVR render with this guessed transfer function should closely resemble the design exemplar. Similarly, we can use a neural encoder to replace the role of the DVR expert and a neural generator to replace the role of the DVR render. During training, for each iteration, we sample a batch of image triplets, which includes a design exemplar, a viewport image, and a ground truth image. The ground truth image is rendered with the transfer function the same as the design exemplar, and the viewport the same as the viewport image. During the forward propagation, the encoder maps the design exemplar into a latent code. The latent code and the viewport image are then fed into the generator to produce a neural rendered image similar to the ground truth image. The loss term is computed by combining the adversarial loss given by a discriminator and L1 loss. Once the latent design space is obtained, users can explore it with a set of interactive tools we proposed. Similar to the original design gallery method, we provide the users with an outline view and a history view. The query view allows users to upload an image to query the closest design. To achieve this, we use the encoder to map this image to a latent code in the latent design space. For example, we can use an arbitrary DVR image as input to obtain the similar design. Then we can even make some simple hand drawing on it and query again to obtain the corresponding new design. In the navigation view, the user can select some design exemplars from other viewers to generate a design subspace among them. Users can use intuitive navigation operations like panning, zooming, and scaling to explore this design subspace. The modification view is designed based on the finding that many semantically meaningful directions can be discovered within the latent space of generative networks. For example, the user can find a semantic direction of adding blue skeleton within our interface and apply it to any design exemplar. In the reconstruction view, the user can reconstruct the explicit transfer function from a neural rendered design. This is realized by a differentiable DVR render. Here, the transfer function is the only optimizable scene parameter. The optimization loss is computed by combining the L1 loss and a transfer function smoothing loss. Here we show a case study for using our interface.
The user first uses an image rendered by other researchers to query a similar design within the design space. The obtained design exemplar is quite similar to the query image. Then, the user delves into the local area where the obtained design exemplar is located, in order to explore more relevant design exemplars. Next, the user chooses some design exemplars to create a design subspace among them. The user navigates this design subspace and finds some interesting patterns. Then the user decides to start creating his or her own design. The user first chooses this blue tooth of interest as a starting point. The user finds the color is too cold, so the user modifies it toward another tooth with a warmer color. However, now the pulp of the tooth is too significant. So the user makes some manual changes to cover the pulp with a background color, and uploads it as a query image to obtain a design exemplar without pulp. Now the user can modify his or her tooth toward a tooth without pulp. The user also wants to add another feature to his or her tooth. To achieve that, the user finds a direction in the navigation view of the semantic "add this green feature" and uses this direction to modify his or her tooth. Now the user has obtained the desired design. Finally, the user can reconstruct the explicit transfer function based on his or her design. The rendering result with the reconstructed transfer function is also similar to the target design.
We evaluated the generation fidelity of our approach on 5 test datasets. The quantitative metrics indicate that overall our architectures can successfully perform the imitation task. The qualitative results also confirm this. We also conduct a series of experiments to investigate how different factors affect the generation fidelity. Please check out our papers for more details on this. Our experiment on transfer function reconstruction shows that the reconstructed rendering result closely match the reference. And we found the generator and the differentiable DVR render can complement each other. That is, the generator provides a rough direction for optimization, while the differentiable DVR render can remove the artifacts produced by the generator. In conclusion, we propose differentiable design galleries, an image-based transfer function design approach. We present that combining generative networks for design space exploration and differentiable renders for faithful visualization generation could be a promising research direction. And we believe this approach has the potential to be extended to more complex volumetric data and more advanced exploration methods.